Bismillahirrahmanirrahim. Previously, we started to discuss Diels-Alder reactions. We described the basic prerequisites, the requirements of the reactions. In that very aspect, I've told you that the Diels-Alder reactions are important because they produce a cyclic product. The product in such reaction is supposed to be a cyclic. You started off from reactants which do not carry any ring, a cycle, but when you react them together, the simple rearrangement of the pi bonds generates six-membered cyclic ring. So if you want to generate a six-membered cyclic ring, then you can take the help of the Diels-Alder reaction. For such reaction, I've told you, the requirement is you should have a sort of an alkene, and then you need one dienophile, the one which carries one double bond, and then you need diene, the one which carries two double bonds. Today I want to discuss the stereochemical aspects. Stereochemical aspects of Diels-Alder reactions. Stereochemistry involved. In the previous lecture, I gave you a bit intro about the stereoisomerism and how they could influence the reactivity of the Diels-Alder reactions. Influence, they cannot take part, but they just could influence, mean either they could make the reaction faster or they could slow down the reactions. Okay, so we discussed that this body should carry electron donating group. However, this body, the dienophile, should have electron withdrawing groups. That favors the Diels-Alder reactions. Then I have discussed a number of examples where your dienophile could have different substituents. They could be present in cis form or they could be present in trans form. Let's say I'm writing here two chloros are present in trans form. They are in opposite direction. Two chloros are connected on the alkene onto opposite directions. So means they are in the transposition. So what happens during the reaction? Trans groups on an alkene, how they will rearrange themselves in the product. That's what I'm going to discuss with you guys. So as I've told you, this double bond moves over here to make a bond between this carbon and this carbon. This double bond moves in between the carbon number 2 and the carbon number 3, and then this double bond between this carbon and this carbon moves to this carbon moves here to make the double new bond. So as a result, you have this type of compound. We have an idea this carbon carries this chloro, and we have another chloro group which is supposed to be in trans form, in transposition actually. So we can write this body as, we can write one body in bold bond, we can write the other body in dotted bond. It represents these two chloros are in, one is into the plane, the other is out of the plane, mean they are in trans position. They are trans to each other. So the groups which are present on dienophile, we can write them trans by keeping one bond as bold, the other one as a dotted. When these bonds in trans form, however, when the situation is that the two of the bonds were in the same position, let's say the chloros are on the same side, mean it's a cis bond, it's a cis alkene, both chloros are on the same side, then one can imagine we need to write these two chloros on the product. They are supposed to be on the same side. We can write both of the chloros in bold form like this. When they are in the cis form, mean on the same side, we need to write them with bold bonds, or we can write both in dotted bonds representing that these two bodies are on the same side, they are cis. So when cis, either both should be in bold or both should be in dotted bonds. Once they are present in trans geometry, they are trans isomers, mean the alkenes are trans, then we need to write one of the bond as dotted and the one as bold form. Then it will be cis or trans, I'm sorry to say, the other will be, or it could be written something like that. We can write the same product like either both dotted, something like that. It represents that. Or we can write both in dotted bond. It represents the same product. It's the same product, you know. So this is how the stereochemistry is involved in Diels Alder reactions. The stereochemistry of dienophile. It could be the simpler groups, or they could be some sort of the complex substituents are around. As I've told you in the last lecture, let's say we have this sort of two phenyl substituents around, two benzenes are present around this double bond. So at the moment two benzenes are cis to each other, so we can write them in the same direction, same, then we need to have both like bonds, and then we can write in the benzene something like here, and then we can have the benzene something like here. Once they are in cis form, if the benzenes are in opposite directions of the starting material, one is on this side, the other was on the other side, then we can write the dotted bond for the other benzene. So this is how the stereochemistry, nothing is happening around this area because nothing has been involved in this diene. At the moment I'm trying to convey you guys the effects of the stereoisomerism of the dienophile. It can be only two forms, either cis or in the trans. Whatever is the original stereochemistry of the dienophile, it will be retained. Cis will remain in the form of cis, trans will remain in the form of trans around these two carbons. No change. Stereochemistry, no change in stereochemistry of the dienophile. I could write it as no change in stereo chemistry, stereochemistry of the substituents of dienophile. the dienophile stereochemistry remains unchanged. Cis will be on the cis, the trans are supposed to be written on the trans form. How cis and trans? If you want to show the cis isomerism, we need to keep the both bond in the same form, either both bold or both dotted bonds. It means it's a cis. If we write one as a bold, the other as a dotted bond, then it means they are in trans form. They have the trans stereoisomers in the form of a dienophile is in the form of a trans isomer, So this is how we need to write. This is what about the stereochemistry and its effects on the product. On the other hand, if we have different stereoisomers involved, let's say if the diene which is involved in Diels-Alder reaction, let's say it's a diene, its own stereochemistry. It should be in cis form, It is a prerequisite, it's a basic requirement, fundamental requirement for the Diels-Alder reaction. The diene, it should be in cis form. It can be in trans form, like if you like the two double bonds in this form, it's a double bond in this form. It's a trans. It's a cis. It's a cis form, it's a trans form. Both are alkenes, dienes, It's a dienes. 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons. For Diels-Alder reaction, the dienes are always supposed to be cis. The trans, they never undergo Diels-Alder reaction. So you are supposed to be very clear about that. The trans, dienes, they never undergo Diels-Alder reaction. For Diels-Alder reaction, the alkenes are supposed to be in cis form. Both of the double bonds are supposed to be on the same side, both of the same side. If they are on the same side, then they can move around, then they can move around to give you the product. If they are present in trans form and we have this form, then movement of this one and then the rotation of this bond will be difficult, It's a difficult. It has to be converted first into cis, then it can undergo into the into Diels-Alder reaction. So trans, they never undergo Diels-Alder reactions. Only the cis dienes, they are supposed to be the participants in the Diels-Alder reaction. So I have discussed two aspects with you guys, the stereochemical aspects. The alkenes, we have an idea, they show cis and trans isomerism. In Diels-Alder reaction, there are two components. One is diene, the other is dienophile. About the dienophile, I've told you, it can be in cis form, it can be in trans form, no problems. This can be in cis form or it can be in trans form, no problems. Whatever the form is, it will remain the same in the product, no change. If cis, you need to write the both bonds in bold form or in both in the dotted form. If they are trans, then one bond could be the dotted, the other could be a bold one. So no problems. We can deal with the stereochemistry, stereoisomerism of the dienophiles. However, in case of dienes, it is always supposed to be cis. If it is present in the trans form, then it cannot undergo Diels-Alder reaction. That's a very much basic requirement. Sometimes, if you have a dienes which are in trans form, trans, as per the reaction requirement, they cannot give us the products. Let's say you have this sort of diene. It cannot undergo into the Diels-Alder reaction. Then what we do? We heat them simply. We heat them. By heating, the double bond gets rotation. It rotates around the carbons and the strands converts into cis first, and then it participates in Diels-Alder reaction. So trans dienes in the beginning, they are not useful. They don't participate in Diels-Alder reaction. So what one could do, one can heat it up to a bit higher temperature so that trans can be converted into cis. After its conversion, it will be ready to react with the dienophile to give Diels-Alder reaction as per usual, as per normal. So there won't be any problem. So this is one of the aspects of the stereochemistry with the diene and the dienophile. Let me explain another thing to you guys. Let me start with dienophile again. Let me keep the diene simple. No substituent at carbon 1, 2, 3, 4. No substituent. Let me keep it simple so I can make it a bit more easier for you guys to understand. I'm just dealing with the dienophile actually. This is a sort of a dienophile. That's a sort of a ketone. Carbon 1, 2 carries this sort of. It can be a dienophile. I've told you yesterday there are different types of dienophiles. Whatever the requirement finds a double bond that makes somebody a dienophile, So what happens then? It goes here, moves here, it moves here. Okay? Then what it gives us? It gives up something. It is something like that. So this double bond moves over here, so it goes like this one. This bond moves over here, so it closes over here. So this will be the product. There are two chances. When such two reactants, you put them in the flask and stir them, heat them, they get the energy. This dienophile has the chances to react with this body in two ways. One way is the same. It can react with the diene in one way, the way I have discussed with you. The other way could be, the way number 2 could be, let's say, no change in diene because it's the same. From where you start, carbon 1, 2, 3, 4 is the same. Either it moves, let's say, this double bond this side, if it reverts this or this way, no issues, no problem, it's the same. However, it could produce some different example. Let's say in the beaker, sometimes it's present in this scenario. The other way it could be present in reverted position like this. It has got reverted. In the flask, in the beaker, it got reverted before it collided with the diene. It can be in this form, it can be in this form. In this form, still the double bond is there, so it's a dienophile. The double bond moves and gives you a product. No issues, no problems. The other way, it could be in this fashion. Again, it moves in this way. This moves over here, this bond moves over here to give the product. Over here, no, this is present at this carbon. So the body is supposed to come over here. So either it could be on the upper side or it could be on the lower side. Whatever the situation is, in fact, both are the same, both products are the same. But to make it a bit more convenient, let's say, this product carries this functionality. On the upper side, this carries on the down side. But in fact, as a chemist, in case of its chemistry, numberings, names, nomenclature, both are the same. But it can happen this way. Why we need to discuss? To clarify in my next example. This is how it could be. Is that fine for you guys to understand? Because whenever you ask the molecular reactants in the flask, they can keep any symmetry. They can be present in this fashion or they can be present in this fashion. They can take with each other to give you product. This is the case when there is no difference over here. In the present of this way or the present of this way, both are the same. But in this case, it can be different. Apparently, but it is not in fact. Let me explain the other. So this is the case. Let me get back to explain it again. Let's say if we have a substitute here, it's a form of a chloro at the carbon number 1. Over here, then again it can have two possibilities as well. Either it is in this form or it can revert itself in the flask to have this fashion as well. It is possible. Both are possibles. Let's say the possibility number 1 and this body remains on upper side. Then again it moves over here, this moves over here, this moves over here. So product carbon number 1, this one is here. So it will have a chloro around here. Is that okay? Similarly, if you look into the one, it's a method number 1, the case number 1, the way number 1. This is the way number 2, the reaction way number 2. Let me get break for a. Yeah, I was explaining to you. In this chloro is present on carbon number 1 of the diene. It can be in this position or in this position. Both in fact are the same. But for a while you can imagine it is in this fashion, then it gets reverted. Then this could be possible, this could be possible. If this is the possibility, then this chloro is supposed to be on this carbon over here. Basically there is no difference between the two products. You can imagine carbon number 1, carbon number 2, 3, 4, 5, 6. Similarly, it will be carbon number 1, carbon number 2, 3, 4, 5, 6. So 1, 2, 1, 2. No issues, no problems. The same products. Is it clear? I hope you got my words. What I'm trying to convey you, the diene or dienophile, they can have a reverted position inside the flask. If that gets revert, then it can affect the product. It can give you a bit different product. But at the moment what I have discussed, the product is supposed to be same. But gonna be different now. Let's see. If the reactants are substituted, let's say on the carbon number 2 at the moment, over here. If this is the way, then what happens again? This bond moves here, this comes over here, this goes over here, but this chloro then will be at the carbon number 2. And this carbon 1, 2, 1, 2 from here, so it will be something like that. Similarly, if it gets inverted, this goes over here, so movement of the bond from here to here, here to here, and then here, it gives you the product something like that. So this is how the two products are. Again, the products are same again, because let's say carbon 1, 2, 3, 1, 2, 3, they're supposed to be the same. However, what happens then? If they both gets inverted, one of them gets inverted, the other remains the same. Let's say this body is here and this is in this position. In this position means this is original position, this one here, this one here. Movement, this is the product. In the next example, if this goes to revert, one of them reverts but the other remains the same. What I'm doing, I'm reverting it as well as I'm reverting it this one. If you revert the both, if both of the reactions revert inside the flask, then the product will be the same. If one of them reverts, let's say this is body and this remains same, originally this is here and this is here, they react with each other to give us this one. No, this remains the same, but it reverts itself. Then what happens here? It moves over here, it moves down over here, it moves over here. So what will be the product? In this case, it's chloro number over here. In this case, the chloro number, this will remain on the same side, something like that. And the chloro will come over here. So now this is the difference. The big difference has come up now. It's carbon 1, 2, 3. In this case, 1, 2, 3, carbon number 4. Two different products are available inside the flask. Two different products are available inside the flask, you know. When, again I'm repeating for you guys, you have two reactants. One is diene, the other one is dienophile. They can react with each other in a positive way, that's okay. Then what happens? During the stirring, both of them gets reversed, then react with each other, they produce the product. In both cases, the product is supposed to be the same. Once, when they are in the same alignment, when both of them revert their alignment in the flask, case number 1, case number 2, products would be the same I was told you. The other case could be two of them reacts, but one of them reverts, the other one don't. The other one doesn't revert, the one reverts, you know. Then two cases, two products, this product and this product is possible, you know. In such cases, which one is supposed to be the dominating one? One will be the major product, the other will be the minor product, the product which you will receive in small amount. Two are possible, this way or this way. One will be the major, the one will be the minor product. Which one will be the major? That matters. One has to find why one major, the other one is supposed to be the minor. I will explain. Let me make it very clear again. I think I'm not messing it up, but trying to convey you guys. Let me get back. The substituent has the carbon number 1 on the diene. Let's see. You have chloro over here. You reacted it with this body. Okay, moving here, moving here, moving here, so we can have a product. I don't think so you have any problem. This chloro will be at the carbon of this. This is next one, so it is supposed to be this way. Is that fine? The other way could be, if this body gets reversed inside the flask as a result of stirring, this body gets reversed, you know. So what happens then? We have an alkene like this, having this chloro, the other is supposed to be in the same direction. No change, no revisions, no reverts. Again, what happens? This goes this way, this goes this way, this goes this way. So what will be the product? The product will be something, it remains on the same side, it comes over, it comes on the carbon number over here. It's supposed to be here, on this side. Is that fine? In this case, it moves here, the carbon number 1 carries this one, over here it carries this way. So, half a difference between the two. 1, 2, 3, chloro has come on the carbon number 3, over here the chloro is on the carbon number 2. One can say it's ortho product. Ortho product. Under these circumstances, if two products are possible by the revision of the one of the reactants, then are those are supposed to be the major product. That will be the major product. I could highlight it. It is supposed to be the major, and this will be considered as minor product. Okay, so you will have a minor product, this body, and this will be the major product, you know, the one where chloro is closer on the carbon number 2. So this is how the stereochemistry of the diene and dienophiles do influence the reaction rates as well as the outcome of the reaction. Outcome of the reaction means the product. Two products are possible, this one and this one. This is supposed to be the major, this is supposed to be the minor. This is a case when your diene or dienophile, they contain the substituents, and there are chances that those substituted dienes, they revert their position inside the flask during the chemical reaction. When you put dienophile in the flask and you stir them together, they can be in this fashion, or one of them can revert here to get the to make the product, or it can be in the same position, this can get revert. If it gets revert again, then the same products are supposed to be there. So this is how the stereochemistry is involved in Diels-Alder reaction. Diels-Alder reactions are those reactions which gives a cyclic product. Starting from linear chain reactants, we receive cycles, you know. Secondly, this reaction happens only with the rearrangement of the pi bonds, no byproduct formation. So that's why they do come under eco-friendly reactions, green reactions. And what are the requirement of the reaction? Only two. There should be a diene, an alkene having two double bonds, and then a monoene, mean a dienophile, the one which carries only one double bond. If they are available with you, you can react them to get the product having cyclic ring with one double bond. And this is how you can use Diels-Alder reaction as green reactions for the preparation of products at lab as well as at industrial scale. So this is how I have tried my best to explain the stereochemical aspects of Diels-Alder reaction. I will have another follow-up lecture on the same topic to cover a few more concepts, especially regarding the stereochemistry. I hope you got the basic idea. If you have any problems, any questions, queries, you may put those in comment area. You can approach me through WhatsApp or send me an email. I will try my best to respond to you at the earliest possible, inshallah, and help. We'll be happy to help you guys. Thank you very much. Assalamu alaikum.